All right. So for homework, I asked you to simplify some trigonometric expressions. So the first one we had was cosecant of theta minus cosine of theta times cotangent of theta. And the second one, I used a different variable here. This is a Greek letter phi, P-H-I, phi. It's just another variable we use for angles sometimes, depending on the situation. A lot more times you'll see this in physics if you go that route. But it's just another variable, right? Any letter can go there. All right, so that is cosine squared of phi over 1 minus sine of phi. And I gave you a hint there that this one is a little easier than you might think. So let's see if you found these. All right, so remember, there is more than one way to tackle this, and you may have ended up with a slightly different answer. All right, just ask yourself, is this as simplified as I can get? Right? You know, is there anything else that I could divide? Is there anything else I can combine? So with this, you know, I don't want to say that there's no wrong answers, because there are wrong answers, but there may be multiple correct answers. All right. So the first one we have cosecant minus cosine times cotangent. So right off the bat, I don't see any squares, so I'm not going to be using any Pythagorean identities right now. I know that cosecant is 1 over sine. Maybe that'll help me, maybe it won't. But over here, I'm seeing some things that might work out. The cosine, remember I told you, one of the good things, or one of the better ways to handle this, I'm blanking out on words right now, is to get everything in terms of sine and cosine, right? Because those are our most basic trig functions. You can't really break them up any further, and they're easy to work together with, right? So the cosine is going to stay cosine. But what I'm going to do is, because it's not a fraction, I'm going to put it over 1, right? Any of our, that's one of the rules. We could always put something over 1. Now, cotangent, we have the quotient rule. Cotangent is cosine over sine. All right, be careful. Tangent is sine over cosine. Cotangent is cosine over sine. That's a quotient rule. So I'm going to multiply these over there. Now this is still going to be 1 over sine. I'm not touching that. But now I have cosine squared over sine, right? I multiply those two together, and I multiply that. 1 times sine is sine. Now I'm dealing with subtraction of fractions. Luckily, they already have a common denominator. So in the numerator, I have 1 minus cosine squared over sine. Well, before I didn't have to worry about Pythagorean, but I have a 1 and a cosine squared. So, okay, one of the things we have to worry about is sometimes, you know, we have to manipulate our Pythagorean identities, right? So I can't go ahead and just substitute in anything right now because I don't have 1 minus cosine. But if I subtract cosine from both sides, 1 minus cosine squared is sine squared. So this I can replace with sine squared over sine, right? And this is like I said, treat this like variables. This is like x squared over x. So simplifying that, we are just left with sine of theta. So we have, I'm just going to rewrite it, cosecant minus cosine cotangent. All of that is just equal to the sine of theta. Right? And that's as simplified as we are going to get. I cannot simplify it any further than sine. Okay, any questions about the first one? You may have taken a different approach, but if your final solution is sine, you're good. All right. For the second one, this one there is definitely multiple ways to do it. With the way we learned yesterday, one thing I can do is I can multiply by the conjugate. Right, and that would get me some things. But in the numerator, then I'd have a lot. I'd have cosine squared plus sine times cosine squared. That's too much. Right, I'm lazy. I don't want to do all that work. What I do see, though, is this cosine squared. So again, I'm going to use my Pythagorean identity. Oh. And I'm going to manipulate it so I get the cosine squared by itself. So this I'm going to use for substitution up here. So my new equation is going to be 1 minus sine squared of phi over 1 minus sine of phi. Now they look very similar, but be careful. This is a squared and that is not. This, though, is a perfect square. All right, so again, if I used variables, I could write it as 1 minus x squared, which I can split up to 1 plus x times 1 minus x. So my numerator here, I can rewrite that as 1 plus sine times 1 minus sine, all over 1 minus sine. Now, this denominator matches exactly with that numerator, and they eliminate each other, and we're left with 1 plus sine of phi. I'm just realizing now that I asked you to type these in, and typing in a phi is really hard. So if you want to type it in just using x's, 1 minus sine, or I'm sorry, 1 plus sine of x, that's fine. Or if so I know some of you like to email me your work, so that's okay as well. All right, so your final answer for the second one was 1 plus sine. Any questions? All right, let me just, I don't know what I did with the notebook. Okay. All right, so today we're kind of moving along. It's in the same wheelhouse. But now, like I said, it's going to be actually a little easier. Verifying trigonometric identities. So with this is similar to simplification, but now we know what the end goal is. Okay, I know where I want to go. So let's just start with an example because it's really kind of self-explanatory, especially with what we just did. Let's see, I'm trying to pick a good one here. Okay, let's do that one. All right, so here we are looking to verify that secant squared of theta minus 1 over secant squared equals sine squared. So like I was saying yesterday, this one is a little more straightforward because you know what you want. Okay, they're just not telling you to just to simplify and hope for the best. Okay, you have an endgame here. You know what you want your equation to look like. Now, the somewhat tricky part is you have two sides, right? So what side do you manipulate? Usually it's kind of a rule of thumb. Whatever is your simpler side, you're going to leave alone, and you manipulate the other side, right? So this sine squared, I can do some stuff with sine squared, but that's pretty basic, right? Sine is one of our base functions, and it's just sine squared. There's nothing else too fancy. So I'm going to leave this by itself, and I'm going to keep manipulating this until it looks like that. All right, so that's all we're trying to do. I want to simplify this so it looks like that. So we're going to use some of the rules that we've been doing. Maybe along with today's lesson, I'll put up a rule, like a chart of all the trig identities, just so you have an easier reference. Like I told you, you feel free to look them up as you're doing it. I'm not expecting you to remember every single trig identity. Hopefully with usage, it starts sticking a little bit, but this is, all brand new content for you guys. So, if you don't remember that, you can replace secant squared minus 1 with tangent squared, that's okay. I'll give that to you. All right, so like I just said, the first thing that we see is, I have a secant squared and a 1, right? I have a trig function squared with a 1. So that tells me I may be using a Pythagorean identity. Now, again, the tricky part with the Pythagorean identity is they don't always look like what we have them as, right? So I have a secant squared and a 1. So you tell yourself, all right, that's a Pythagorean identity. I'm not sure what it is. So what I would recommend is write down somewhere, or, put a star next to it on your reference sheet, the rule that involves secant and 1, right? So the identity that we're going to use is 1 plus tangent squared equals secant squared. So what I want to do now is I want to manipulate this. So somewhere I get something that looks like this, right? So I want secant squared minus 1. So with this here, if I move the 1 over, I get secant squared minus 1 equals tangent squared. So that's telling me I can substitute tangent squared where I see that, right? So I'm going to rewrite it, tangent squared over secant squared. Now, if you want to be super formal, you can write sine squared. But if you do that for every step, that's a lot of writing sine squared. So what we do is we kind of forget about it, right, until the end. All right, so now what can we do with this? I have tangent squared over secant squared. Well, secant is one of our reciprocal functions. So I know that 1 over secant, right, because secant's in the denominator here, 1 over secant is equal to cosine. Now, I'm writing these just so you guys have references. As you're doing this, you don't have to write the actual identity out. It might be helpful for you if you want to organize your thoughts, right? The equation's over here, the identity's over here, something like that. But I'm not making you do that, so that's up to you. So this tangent squared, I'm not doing anything with that right now. So that's going to stay tangent squared. And since 1 over secant equals cosine, if I split this, this would be tangent times 1 over secant squared. Secant squared would get me cosine squared. Okay, so from here to here, I just use the reciprocal rule. That's secant squared. 1 over secant squared is cosine squared. And again, because secant squared is in the denominator, that lets me bring it up as a cosine. Then, okay, so I have a cosine, so that's pretty basic. I can't go any further with that, right? I mean, I can use a Pythagorean identity, but that would just be making things a little more complicated. I'd be making it larger, right? We're trying to condense it. We're trying to simplify it. So although tangent is pretty basic, it can still be broken up. And, you know, we're looking for a sine. We're not looking for tangent. Right, so our quotient rule tells us that tangent is sine over cosine. So tangent squared would be sine squared over cosine squared. And I still multiply this by cosine squared, and I'm just going to put it over 1. Well, now I have a cosine squared in the denominator here, and a cosine squared in the numerator there. And what are we left over with? Sine squared of theta. Right, so we verified it. I don't think you really have to say anything after you find it. Right, so just as long as you end up with what you had on the right side or on the left side, depending on what side you were working with. You could just say verified, you could put a check mark next to it, whatever you'd like. Okay, any questions with that? All right, now there are 2 other ways that you can verify identities. They're not as thorough, but you know, for mathematical purposes, they're good enough, right? And they both involve using the calculator. Oh no, one is. Right. So what you can do is there we go. Okay. What we can do is we can plug both of these equations into your y equals, right? So if you have, you know, if you're using Desmos, right, you would just type it in as 2 different functions. So I'm going to use, actually, so that would be a lot of work with this. So actually, I'm going to use Desmos because there's no secant button on our on the calculator. So I'm going to type in secant squared of x, no, squared of x minus 1, all divided by secant squared of x. All right, so there is my first function, secant squared minus 1 over secant squared. And on the other side, we had sine squared. And look at that. All right, if I mess around, I notice that they overlap each other. Right, they are the same exact equation. So you can look at the graph, right? And if they give you the same line, then you have equivalent functions. The other way we can do it, I don't know if they let us do it here. I think I can do it on the GeoGebra, but I don't know about here. The other way you can do it is you can look at the table, right? So I'll just do something simple here. So if you had, sine of x squared, so I'm going to use a basic Pythagorean theorem, sine of x squared. And I know that that is going to be equal to cosine of, no, I'm sorry, 1 minus cosine of x squared. All right, so again, if I look at the graphs, it's a tiny graph, but there's my first function. And my second function doesn't look like it's appearing because it's the same function, and my battery's died. Awesome. And 1,000 today. Okay, those were good batteries. Good. All right, let's go back. All right, and so again, I can look at the graph, right? They're the same graph. So on this kind of calculator, it's a little difficult. Let me just change the window so it looks nice. All right, there's my first function. It kind of bounces along the top. And my second function, again, it's the same thing, so you don't see it. But if we look at the table, right, our y1, which is the first equation, and our y2, which is the second equation, all those match up for each x. Right, so as we go along, right, at 6.5, it's the same. At 7, it's the same. At 7.5. So those are just other ways that you can make sure that you're not just on some wild goose chase and, trying to make two equations equal to each other when they don't. Right, so I can plug them both in. I say, all right, look at that. According to the graph, according to the table, right, they're equivalent. But for mathematical purposes, we use this method because it's a little more succinct, right? We can actually prove it. All right, so I'm going to give you one problem to try tonight, and then we'll start tomorrow by going over that.